Today we will go for 10.2 and 10.3. Maybe with 10.4, but I'm not sure. I don't want to rush it. Now 10.2, calculus with parametric curve. First one on derivative, on tangent. So 10.2, calculus with parametric curve. Now, first one is on tangent. Let x be a function of time and y is the function of time. That gives us parametric curve. Then dy dx is actually dy dt over dx dt. Spring 20 test 2. Spring 20 test 2. Let me see if I have it. Give me a second. Spring 20 test 2. Do I have the solution? Yeah. Yeah, let me post it. Thanks for reminding me. Where is that? Is it here? It's on the discussion board, huh? Spring. Where is that? Where's that? School. Spring 20 test 2. Is it the one? Okay. So, yeah, it's posted. Not that one. It's this one. So basically, this is equals to the dy dx is the derivative of y respect to t divided by derivative of x respect to t. You can call that chain rule. Yeah, you can call this chain rule. But this is, you can also call this, what's called, it's a special form of L'Hopital rule, actually. So you can call that chain rule. You can also call that L'Hopital rule. Now, the tangent line, horizontal tangent line, the tangent line is horizontal. Is associated to the situation where dy dt is 0, but dy dx dt is not 0. In other words, the numerator is 0, but the denominator is another number, such that it becomes 0. Dy dx is 0, represent horizontal tangent line. Now, vertical tangent line. Vertical tangent line the tangent line is vertical if dx dy is 0, right? But dx dy is basically dx dt divided by dy dt. Okay, now we have vertical tangent line if dx dt is 0, yet the denominator dy dt is not 0. Okay, with a note. If we get dy dt equals to dx dt equals to 0 at certain number, let's say at t equals to t1, then apply limit condition of dy dt and limit of actually apply this to be more precise. Apply that dy dt over dx dt and or depends on what you're looking at, horizontal tangent line or vertical tangent line. So instead of replacing the t directly, we use limit condition. Now, how about the second derivative? The second derivative is the derivative with respect to x of dy dx. But by chain rule, this is the derivative of dy dx respect to t times dt dx. That's by chain rule, which basically means the following. That's the derivative of dy dx respect to t divided by dx dt. Okay, so that's the second note. The third note, the area. If you have a curve, let's say the curve is from t equals to a to t equals to b. Now the area is supposed to be integral of the domain y dx. Is it right? That's what we learned before. However, we will parameterize the y. That's basically yt. And the dx is basically dx dt times dt. Okay, where the t is from a to b. Or you can also do integral from a to b of xt dy dt times dt. That's the area under the curve. How about the arc length? I just give you all the formula, arc length. The arc length L is integral of ds. Now we learned this before. This is integral of dx being squared plus over the domain D, dy squared. But we cannot integrate that. So we will divide each one of them by dt squared, dx dt squared plus dy dt squared times dt. I hope you noticed that. The work is basically like this. The work is basically like this. We have dx squared plus dy squared, right? Okay, multiply this by dt over dt. But I will express the denominator as square root of dt squared. You see what I mean? Now then you put that in. Like that. Okay, so you see, it's basically you need to memorize the original pattern for the integral, and you adjust that with the parametric equation. Adjust that with parametric equation. And that's it. We are basically done with this section. Now, the rest are applying what we learned. Now, suppose, for example, would you like to pick any questions from page 675? Let me do number 2 first, the easiest question here. So we have the curve is given by x equals to 1 over t, and the y is square root of t e to the negative t. So the question is find dy dx. So dy dt first, dy dt, the derivative of y respect to t. That's 1 over 2 radical t e to the negative t minus square root of t e to the negative t. I think I can factor square root of t e to the negative t over 2. So I get t, I'm sorry, not t, 1 over t. You know what? No, I factor this at the bottom instead. That's the lower exponent, 2 square root of t. So I get t here minus 1. And dx dt equals to negative 1 over t squared. So dy dx will be e to the negative t times t minus 1 over 2 square root of t divided by that, or multiplied by the reciprocal. So I will get negative t to the power of 3/2 with 1/2 e to the negative t, t minus 1. Actually, from here, we can go on a little bit Find, suppose I have follow-up question. Find the coordinate on the curve whose tangent is horizontal. So basically we need the dy dt to be 0, right? Now the reason I factored that earlier so that we can see the zeros a lot faster. Now this is equals to 0 if t minus 1 equals to 0. No other way, because e to the negative t can never be 0, right? So it is 0 when t equals to 1. And make sure you check that dx dt when t equals to 1 is not 0. Okay, so the curve has horizontal tangent at t equals to 1. But when t equals to 1, what's the coordinate? So x, y, when t equals to 1 is, the x is 1 over t, so that's 1 over 1. The y is radical t e to the negative t. So the coordinate is 1, 1 over e. Okay, that's for number 2. Now, let's see next, let's say number 8, or number 6, I mean. Or do you have any question you want me to do? So the curve is x equals to sine cube theta. The y is cosine cube theta. And the theta is pi over 6. Find the equation of the tangent line. Find the equation of tangent line. At theta equals to pi over 6. Let's find the coordinate first. So when theta is pi over 6, that's sine cube of pi over 6. Sine pi over 6 is 1/2, as I believe. Make it cube, that's 1 over 8. Don't make it decimal. You may end up with a lot of rounding error. Y pi over 6 is cosine cube of pi over 6. That's radical 3 over 2 cube. That's 3 radical 3 over 8. So the coordinate is 1/8, 3 radical 3 over 8. Next, we need the derivative. So dx dt is 3 sine square theta cosine theta. So dx dt at I'm sorry, not t, theta, not t. At theta equals to pi over 6 is 3 times sine squared pi over 6 cosine pi over 6. That's 3 times 1/2 squared times radical 3 over 2. That's 3 radical 3 over 8. dy d theta equals to 3 cosine squared theta times negative sine theta. So dy d theta at theta equals to pi over 6 is negative 3 cosine squared pi over 6 sine pi over 6. That's 3, 9. That's negative 9 over 8. Okay, so dy dx at theta equals to pi over 6 is negative 9 over 8, big over 3 radical 3 over 8. That's negative 3 over radical 3, negative radical 3. That's the slope. So the equation of the line will be y minus y1. What is my y1? 3 radical 3 over 8 equals to the slope times x minus x1. So y minus 3 radical 3 over 8 equals to negative radical 3x plus 3 and plus radical 3 over 8. That becomes 4, huh? So y equals to negative radical 3x plus 4 radical 3 over 8. Simplify. Okay, that's for number 6. Number 8. Because you don't tell me which question to go over, I just randomly pick questions. Number 8, find the equation of the tangent to the curve at the given point by 2 methods. First one, without eliminating the parameter. So let's write down the curve first. Oh, they give us the coordinate, huh? Okay, so the first one without eliminating the parameter. Let's find the t first. Let's find the t first. So what is t such that 1 plus radical t comma e to the t squared equals to 2 comma e. I will look at the x component. 1 plus square root of t equals to 2, right? So square root of t equals to 1, then t must be 1. And we can confirm that with the y component. Okay, e to the t squared equals to e. It means t squared equals to 1, t equals to plus minus 1. From here we see that, so t equals to 1. Now then, we do the derivative. Dx dt equals to 1 over 2 radical t, such that dx dt at t equals to 1 is 1 over 2 radical 1, that's 1/2. dy dt is the derivative of e to the t squared times the derivative of t squared is 2t. Therefore, dy dt at t equals to 1 is 2e, right? When t equals to 1. So dy dx will be, dy dx at t equals to 1 will be 2e over 1/2. That's 4e. Now then, we have the equation. The reason I need to find the t is so that I can use that in my derivative. Okay, but the coordinate itself already found is 2, e. Okay, now then, equation of the line, tangent line, equation of tangent line will be given by y minus e equals to the slope times x minus 2. Y equals to 4ex minus 8e plus e. So minus e here, when I add e, that will be plus 7, minus 7e. That's the equation of the tangent line if I do not eliminate the parameter. Part B. What if I eliminate the parameter? How do I do that? Square root of t equals to x minus 1. Right? So t will be x minus 1 squared. T squared will be x minus 1 to the 4th. So y is equal to e to the x minus 1 to the 4th. Ooh, that's ugly. So dy dx is equal to itself times 4 times x minus 1 cubed. Now when x equals to 2, we'll get e to the 1 times 4 times 1 cubed. So we get 4e. Right? The equation of the tangent line will be the same because the slope is the same. So it seems like eliminating the parameter is easier, huh? That's not always true. That's not always true. Eliminating the parameter may not work that well if you don't get a function. What happened here? what happened here? You still have y as a function of x. You see that? Y is a function of x. But if you don't have y as a function of x, then eliminating the parameter may give us more confusion instead. That's for number 8. Would you like to choose any questions from number 11 to 16? I don't remember which question I have done in my lecture though. So I just don't want to repeat what I have done. So should I just randomly choose a question? Wait, I choose number 13 then. Number 13, find dy dx and the second derivative of y respect to x. And also for which t the curve concave up is the curve concave up. Where our c, our curve, is given by x equals to e to the t and y be t e to the negative t. Solution. See, what I have done so far, just apply what I gave you up there. What I did up here, the theory. Okay, so far I'm just up to here. Okay. Now then, I first find dx dt first. That's easy. Dx dt is e to the t, Mickey Mouse. How about dy dt? Dy dt will be e to the negative t minus t e to the negative t, which I can factor e to the negative t, 1 minus t. Right? Okay, such that dy dx will be e to the negative t, 1 minus t over e to the t, which simplifies to be 1 minus t over e to the 2t. Is it right? Now that's the first derivative. Actually, from here we see that if I do a little follow-up question, the curve is increasing when 1 minus t is positive, right? Because e to the t is always positive, e to the 2t is always positive. Okay, so it is the curve is increasing when t is less than 1. Okay, next, how about the second derivative of y respect to x? Now that is the derivative of dy dx respect to t divided by, you know what, I don't like that notation. Respect to dx dt. So do the derivative of that dy dx above respect to t. over e to the t. So that is 1 over e to the t, that's the denominator that I put aside, times e to the 2t squared, the derivative of the top times the denominator minus the numerator times the derivative of the denominator. So we get, this is 1 over e to the t, here the denominator e to the 4t, on the top we get e to the negative e to the 2t, minus 2e to the 2t, plus 2t e to the 2t. Something factors and cancel. You know what? The denominator is e to the 5t, yet on the top, I get negative 3e to the 2t plus 2t e to the 2t. Cancel 2e to the 2t. Now then, that's concave up. So the curve is concave up when the second derivative of y respect to x is positive. Right? But e to the 3t is positive for every t. So it must be the numerator to be positive. So 2t should be greater than 3. T should be greater than 1.5. Now, follow up. Let's find those important coordinates. Let's find those important coordinates. For example, do we have y-intercept? Y-intercept is when x equals to 0, right? But e to the t equals to, when x is e to the t equals to 0, there's no such thing. Right? Okay, remember our curve is given by x equals to e to the t, the y is t e to the negative t. Is it right? Oh, so when we try to find the y-intercept, we set the x equals to 0. There's no such t. So no such t. So we won't have y-intercept for this curve. How about the x-intercept? The x-intercept, the y is 0. Right? So the y equals to t e to the negative t. When we set this equals to 0, we get it must be because t equals to 0. But when t equals to 0, the x will be 1. That's the x-intercept. No y-intercept, we have one x-intercept. Do we have horizontal tangent line? Horizontal tangent line happens when dy dt equals to 0. Right? Dy dt equals to 0, but the dx dt is not 0. Okay? I think we did this earlier. Yeah, dy dt is 0, 1 minus t over e to the 2t. Set it equals to 0, we get t equals to 1. I need to keep on going back. I hope you don't get confused. So this is our dy dt. Oh, I'm sorry. I took a wrong one. This is our dy dt. 1 minus t e to the t. Is it right? 1 minus t e to the t. But I need to check, make sure that dx dt is not 0. Okay, dx dt, that's e to the t when t equals to 1. That's just e, which is not 0. Okay, so horizontal tangent line when t equals to 1, at what coordinate? At what coordinate? Let me write it here. I keep on forgetting what is my x, what is my y. My x is e to the t, my y is t e to the negative t, right? So horizontal tangent line at e to the 1 and 1 over e. Do we have vertical tangent line? Vertical tangent line when dx dt is 0 and dy dt is not 0. Dx dt is e to the t. Set it equals to 0, no solutions. So from here we see that no vertical tangent line. How about point of inflection? Point of inflection. That is when the second derivative of y respect to x is equals to 0. We actually have that up there. The second derivative is -3 plus 2t over e to the 3t. Set it equals to 0. We get t equals to 3/2. So the coordinate, so x, y, when t equals to 1.5 will be e to the 1.5, 1.5 e to the -1.5. We can approximate this using calculator later on. Or should we? I'll just do it now, just to estimate. That's 4.08 if I round it to 2 decimal place only. And hold on. Oh, I'm sorry, this is 4.48. And this is 0.15 if I round it to 2 decimal places. Okay, the reason I give us do this analysis in blue here, in addition to the one I did in black, to give us a better view when we try to sketch the graph. Now, of course, I will not sketch the graph. I don't even know what it looks like. Maybe I can. No, I don't think I know what it looks like. I can if I want to, but let's take a look on when we try to sketch the graph. Y is e to the t I mean, that's the x. The y will be t e to the negative t. It just looked like that, Thomas. Yeah, it looks like that because my t is only from 0 to 1. You see that? Okay, let me enlarge this. So my t will be from negative 10 maybe, and then up to positive 10. Let's see what happens. That's what it looks like. Let's zoom it in, zoom it out. Yeah, it looks like this. Let's screenshot this. And put that in our here. Okay, where did we say our maximum point? I mean, I mean, the slope, well, when we have horizontal tangent line. Horizontal tangent line at e comma 1 over e. That's approximately in decimal. That's approximately 2.72 and 1 over that. That's 0.37. If I round it to 2 decimal place, 2.72. 2.72 approximately here. You see that? That's e comma 1 over e. That's the vertical line, right? You know what? Let's do this. Going back to this graph here, the vertical line will be, the horizontal line will be, I will add one equation, y equals to 1 over e. You see that? If I super zoom that, should I zoom that even more? It's kind of hard to say, huh? But it's, according to our computation, it's 2.72, approximately here. You see? Okay. And the y component is 0.37, approximately. Yeah, 2.37. Okay, so that's the coordinate approximately here. That's the coordinate where the curve has horizontal tangent line. According to our computation, also we find that, going back to our graph, we have inflection point at at 4.48, approximately 4.5. So the inflection point actually happens around here. So that's e to the 1.5, comma 1.5 e to the negative 1.5. Let me count it again. Somehow I feel like I made miscomputation. So my mistake, this is supposed to be 0.33. Yeah, that's 0.33. And we confirm that we don't have vertical line, the vertical tangent line. Okay, and the curve is concave up when t is more than 1.5. When t is more than 1.5, where is that? Means when t is greater than 1.5. So the curve is concave up to the right of this. Now the one here, it concave down. From the graph only, it's hard to tell, right? Yeah, we can tell it's concave down here, but we cannot really tell where's the cutoff here. Now, according to our computation, it happens when t equals to 1.5. No vertical line, no vertical tangent line. Only one inflection point and only one turning point. That's for my number 13. More question maybe? How about number, should we do number 17 or number 19 or number 18 or 20? You tell me. (18 or 20? Let's do number 18. Number 18, we have the curve is given by x equals to t cubed minus 3t, y equals to t cubed minus 3t squared. Now I will answer the question from the book first. Find the points on the curve where the tangent is horizontal or vertical. I will answer that first. And then from there, I do follow up. Okay, dx dt will be 3t squared minus 3. While dy dt is 3t squared minus 6t. Factor the 3t, I get t minus 2. Okay, so horizontal tangent line, horizontal tangent happens when dy dt equals to 0, but dx dt is not, right? So we set dy dt to be equals to 0. So that's when t equals to 0 and t equals to 2. Now, you make sure you check that with dx dt. So 3 times 0 squared minus 1, that's negative 3, that's not 0, so it's fine. 3 times 2 squared minus 1, that's equals to 9, that's also not 0. So we have horizontal tangent line at t equals 0, which means the coordinate is what? Go back to that when t equals to 0, xy is, I hope you can do it fast enough. When t equals to 0, the xy are 0, 0, right? And when t equals to 2, when t equals to 2, that's 8 minus 12, that's negative 4. Oh, no, that's the y. That's the y. I look at the wrong one. When t equals to 2 for the x, that will be 2, 8 minus 6, that's 2. That's the horizontal tangent line. How about vertical tangent line? That's when dx dt equals to 0, but dy dt is not. Okay, that's 3 times t squared equals to 1, minus 1 equals 0. So we get t squared equals to 1. T is 1 or negative 1. I'll check with the dy dt. 3 times 1 times 1 minus 2, that's negative 3, that's not 0. 3 times negative 1, negative 1 minus 2, that's 9. That's not 0. So we have vertical tangent line when t equals to 1, which means the coordinate is negative 2, comma, negative 2. When t equals to negative 1, what will that be? When t equals to negative 1, that's 2, comma, negative 4. Is it right? Oh, you know what? This is something new for me. This is something new for me. So not new for me, something new for you. What happens? Notice that when t equals to negative 1, when t equals to negative 1, the coordinate is this, right? But when t equals to 2, you have the same coordinate. You see that? Okay, now that's the benefit of parametric equation, because it basically means that this curve may go this way. This curve may go this way. Okay, like it hits the same coordinate at 2 different times. Now the good thing with parametric equation, notice that x and y are both functions of t's. X and y are both functions of t's, yet x and y not necessarily function to each other. So what happened is that you have a graph which is by definition is not a function. X is not a function of y is not a function of x, but we still can treat them as a function if we see them from t's point of view. Okay, that's a nice thing. Okay, so at this point, I already answered the questions for the book. Okay, they want us to find the horizontal tangent line, the vertical tangent line. Now, let me go on with the follow-up. Some standard question. For example, how about the y-intercept? Y-intercept is when x equals to 0, right? That's when x equals to 0. But what is my x again? T cubed minus 3t. That's 3 cubed, t cubed minus 3t equals to 0. T times t squared minus 3 equals to 0. That's when t equals to 0, t equals to radical 3, t equals to negative radical 3. Now plug that into the y. Y is t cubed minus 3t squared, as I remember. That's the y's, right? So what is y at 0? That's 0, that's easy. How about y at radical 3? That's 3 radical 3 minus 9. How about y at negative radical 3? That's negative 3 radical 3 minus 9. So the y-intercepts are 0, 0, 0, comma 3 radical 3 minus 9, negative 3 radical 3 minus 9. Those are the x-intercepts. So it hits the y-axis 3 times at 3 different times at 3 different places. How about the x-intercept? The x-intercept, the y equals to 0. So t cubed minus 3t squared equals to 0. T squared times t minus 3 equals to 0. So either t equals to 0, t equals to 3. So when t equals to 0, x0 is, we know that will be 0. When t equals to 3 for the x, that will be 3 cubed minus 3 times 3. 27 minus 9 is 18. Okay, so the x-intercept will be 0, 0 and 18, 0. We do this analysis first before we do the graphing. Oh, Thomas, you have the graphing software. Why don't you just graph it right away? Well, I want to do my computation and match it with my graph later on. So can I do the computation first? You see what I mean? We have vertical tangent line. We have horizontal tangent line. Let's see if it's possible to do the second derivative. Then we can see the inflection point. Okay, so we have dy dx is equal to 3t squared minus 6t over 3t squared minus 3. We can factor the 3t here and the 3 only here. So t minus 2 over t squared minus 1. Wow, what we are about to do is quite nasty though. So the derivative of dy dx respect to x is the derivative of that dy dx respect to t over dx dt. The top one is the painful one. Hey, but I mean, we can complain but never finish the work, right? Instead of complaining, how about just do it? Okay. So dx dt, that's easy. That's 3t squared minus 3. But dy dx, do the derivative respect to t. So I need to do the derivative of this respect to t. T squared minus 1 being squared. That's at the bottom. At the top, that will be 2t, that's t squared minus t, minus 2t. So 2t minus 2 times t squared minus 1 minus the numerator t squared minus 2t times 2t. You need to be patient also, huh? Okay, so this is equal to, let me bring that down. So 3 times t squared minus 1 times t squared minus 1 squared. On the top, I will get 2t cubed minus 2t minus 2t squared plus 2 minus 2t cubed plus 4t squared. Ooh, wow, that's nasty. 3t squared minus 1 cube at the bottom. 2t cubed cancels. T squared, we get 2t squared minus 2t plus 2. I can factor 2. I think t squared minus t plus 1 is positive definite. This will be strictly positive for every t. How do I do that? Look at the discriminant. The discriminant is negative, but the curve is concave up. I mean, it opens up, right? So it doesn't have x-intercepts. So the numerator is always positive. Yet, if we do sine graph, it has two critical values, -1 and 1. For the denominator, okay, it will be positive here, negative here, positive here. So it will be concave down for t between -1 to 1, and concave up otherwise. Is there anything I'm missing? Horizontal and vertical tangent line, x-intercept, y-intercept, inflection points. We don't have inflection point from what we see here. We don't have the coordinate where the second derivative is equal to 0. Okay, we don't have the situation where the second derivative is equal to 0. The function seems to be continuous everywhere though. Right? It's both of them polynomial. Both of them polynomial. We can say this way. I will do it later on. I'll do it later on. Let's take a look on the graph. Anybody can help me with the x? That's t cubed minus 3t, is it right? Oops. How do I punch in the, okay, minus 3t. And then how about the y? That's 3 cubed minus 3t squared, as I remember. Okay, that's what we have. That's what we see. That's what we have here. We have two y-intercepts. Oh, hold on. Only two? No, according to our computation, there should be 3, right? There should be 3 y-intercept. Let me check again. How many y-intercept we will get? Supposed to be 3 y-intercept. Oh, why we see only 2? Anybody can tell me why? Because the graph is not big enough. Now you see 3. Okay, let's put details to this. Let me screenshot this. It feels good if your computation match with the graph, you know? And that's what I want to present to you. Okay, at least we are right with the y-intercept. There are 3 y-intercepts, right? 0, 0. And what else? A y-intercept 0, 0. And then 0, 3 radical 3 minus 9. And 0, negative 3 radical 3 minus 9. Let me use my calculator to estimate that. Negative 3.8. So this is approximately 0, negative 3.8. And that one is approximately negative 14. See, it's quite good estimate, right? So one of them is 0, 0. And then negative 3.8 for the y component, like the y-intercept, right? Not even negative 4. And this one here is negative 14.2. Okay, and how about the x-intercepts? X-intercept, as we have at 0, 0. And the other coordinates are 18, 0. 18, 0. Okay, how about the horizontal tangent line from the original question at 0, 0 and 2, negative 4. 0, 0, 0, 0, and 2, negative 4. Do you see that? Right? That's the horizontal tangent line. Maybe I use the coordinate instead to point out. Let me use this. So 0, 0, and 2, negative 4. How about the vertical tangent line when at what coordinate? Negative 2, negative 2, 2, negative 4. Negative 2, negative 2, 2, negative 4 again. Okay, now it is concave up. Maybe concave down is better to talk about. Concave down when t is between negative 1 to 1. So let's see when t equals to negative 1, what's that? Have we done that? When t equals to negative 1. So x negative 1 is what? Y negative 1 is what? Oh, we compute that somewhere earlier. No, not yet. Yeah, 2, negative 4. Yeah, we compute that already here. We compute that already. Let me erase this not to bother us too much. So when t equals to -1, when t equals to -1, we are here. When t equals to +1, we are here, right? So it seems like the graph actually, the curve actually moving this way. See, right? You see that? Okay, this is when t equals to -1. This is when t equals to 1. And we get this again when t equals to what? When t equals to 2. The same coordinate there.
Hey, Thomas, I had a question.
Uh-huh.
And I'm pretty sure you already went over it, but
Mm.
it kind of glossed over me. When you have the vertical tangent line or a point of the vertical tangent line and the horizontal tangent line being the same point, when they share a point, what does that mean? Because I don't think I've seen that.
Oh, this is what we have here. It means that when t equals to -1, when
Right.
t equals to -1, it hits this point, right? And
Right.
then when it goes around, when t equals to 2, it hits the same point again, but from different direction.
Oh, right. That makes sense. Okay.
Right? Okay. Yeah. So what we thought was impossible before, now you see it's actually possible. It is not possible if we see that from y as a function of x or x as a function of y. We are not supposed to have that, but with parametric equation, that's the very big benefit of parametric equation. That you may get to the same coordinate at different time. Okay, now that's for this one here. Do I want to do number 20? No, I don't, because I have other things that I would like to do. For example, how about the area under the curve? Let me talk about areas and then arc length, maybe surface area of revolution also. Okay, and then I give myself a break. We go on further. Okay, should I do number 32 or 33? Find the area enclosed by the curve and y-axis. Number 32 or 33? You tell me. Number 32. Okay, so number 32, we have the curve is given by x equals to t squared minus 2t and y equals to square root of t and y-axis. Oh shoot, do we need to graph this first? When in doubt, choose even. And y-axis. I honestly don't know how to do this. I don't even know what the graph look like. So let's do some, how will you do this, Thomas? And y-axis. Y-axis means the x equals to 0, right? So let's say you have a curve like this maybe, okay? So if it intersects y-axis, then we need to find the time when it hits the y-axis. That is when x equals to 0. Okay, so I will set x equals to 0. So when t equals to 0 and t equals to 2. Is it okay? So my t will be moving from 0 to 2. How about that? Again, I still don't know what the graph look like though. I still don't know what the graph look like. I can by trying to, it happens to be something I can eliminate the parameter. So y squared equals to t. So x equals to y squared being squared minus 2y squared. So let me update the graph now. X becomes Y, Y becomes X. So the Y-intercepts are 0, 0, -2, -0, comma radical -2, and 0, comma that. Oh, wow. So it seems like it looks like this. Hold on. No, it looks like this. That's degree of 4. It would look like that. But the thing is, I need to do some adjustment. The Y cannot be negative. The Y cannot be negative. So the graph only, yeah, the Y cannot be negative because of this. You see that? Right? The T cannot be negative. So I get the full graph by eliminating the parameter, but I need to check with the domain of the original parametric equation. So the graph looks like this. Okay, bounded by T equals to 0 and T equals to 2. Okay, so the area will be integral from T equals to 0 to T equals to 2 dt. I move around along Y. So that will be X times the derivative of Y. See, I use this formula. So if I use dy here, this is x dy. The y from 0 to y equals to square root of 2. Right? But then if I change that into parametric, my x will be t squared minus 2t. My dy will be dy dt times dt. Right? That's why it looks like that. Okay, so this is integral from 0 to 2. Let me take the 1/2 out. This becomes 3 to the 3/2 minus 2t to the 1/2 dt. To integrate that is Mickey Mouse. That's 4 radical 2 minus 4 over 3 2 radical 2. That's 8 radical 2 over 2, 1. Huh? Why do I get negative area? Oh, because that's to the left of that. So it should be negative here, negative here, negative here, negative here, negative here. So that's positive 8 square root of 2 over 15. Yeah, because my curve is actually below y-axis, right? Quote unquote, below y-axis, to the left of y-axis. So my area will be this area here, right? I apply negative to make it positive area. Let me take a break, a bit tired. I come back at 8:55. Then I will continue with the arc length and maybe surface area of revolution. And then I go to 10.3, which is on the easy side. Scroll down a little bit. Give me a second. Like this. No wonder I was at the mode of 125% view earlier. Ah. Okay, now this look better, right? Okay, let's take a break. We come back at 8:55. Okay, let me start. That's for number 32. Next one, we did the area. Now how about the arc length? Either number 41, 42, 43, 44. You choose one. Maybe number 42. Number 42, find the length of the curve for x e to the t plus e to the negative t. The y is 5 minus 2t for t between 0 to 3. Okay, solution. Dx dt will be e to the t minus e to the negative t. Dy dt is negative 2. So dx dt squared plus dy dt squared is e to the t minus e to the negative t squared minus 2. I'm sorry, plus 2 squared, plus negative 2 squared. So this will be e to the 2t minus 2 plus e to the negative 2t plus 4. That is e to the 2t plus 2 plus e to the negative 2t. Ah, this one is Mickey Mouse. This is e to the t plus e to the negative t being squared, such that the square root of that is just e to the t plus e to the negative t. Supposed to be in absolute, but both of those terms are positive for every t. Right? So the arc length will be from 0 to 3 of e to the t plus e to the negative t dt. That is e cubed minus e to the negative 3 minus 1 minus 1. So e cubed minus e to the negative 3. That's the arc length. How about number 44? I can do 2 problems because number 42 is too easy. So the curve x is 3 cosine t minus cosine 3t. Y be 3 sine t minus sine 3t. And we want to find the length, arc length for t between 0 to pi. Okay, solution. Dx dt is negative 3 cosine, I'm sorry, sine t plus 3 sine 3t. Is it right? While dy dt is 3 cosine t minus 3 cosine 3t. So dx dt squared plus dy dt squared will be, you know what? Let me factor the 3 out. So it becomes 9 times negative sine t plus sine 3t squared plus 9 times cosine t. It's 9 because 3 squared. So this is 9 times sine squared t minus 2 sine t cosine sine t sine 3t plus sine squared 3t plus 9 times cosine squared t minus 2 cosine t cosine 3t plus cosine squared 3t. So that will be 9 times sine squared t plus cosine squared t. I group it this way. And then minus 18 times sine t sine 3t plus cosine t cosine 3t plus 9 times sine squared t3 plus cosine squared 3t. Do you realize that it's actually more algebra? This is 9 plus 9 minus 18. What's that? Cosine, cosine plus sine, sine. That's cosine 3t minus 2t, 3t minus t. Can I do that? Your trigonometry. So now I get this is equal to 18 parentheses 1 minus cosine 2t. Okay, now then what is the square root of that? Square root of dx dt squared plus dy dt squared equals to the square root of 18 times 1 minus cosine 2t. Notice that I have not touched any integral yet. I have not written any integral. This is all set up. This is all set up. I have issue with this though. How do I take care of this? Now I remember. Double angle. this is square root of 18 times. Let me multiply by 2 and then 1 minus cosine 2t over 2. Do you know what's that? That's sine square t. Right? So cosine 2t equals to 1 minus 2 sine square t. Remember that? Okay, so this guy, oh wow, you need to know a lot of trigonometry. This is 6 absolute sine t. However, sine is positive in quadrant 1, quadrant 2. Now then we go to integral. The arc length, therefore integral from 0 to pi of 6 sine t dt. That's equals to 12. Is it right? Yeah, that's equals to 12. The way I see is this. Integral of sine t in quadrant 1 is 1. From in quadrant 2, the area also 1. You can just do that integration long way. You will get 12 anyway. Wow. You see, the integral itself is like Mickey Mouse, right? To set it up is like, what the? Tedious. Yeah, it's quite tedious. And it's a tricky part here. Yeah, it's tricky part here. Yeah, cos plus sine is cosine of difference. Yeah, cosine A minus B is cosine A, cosine B plus sine A, sine B. Yeah, that's one thing that we need to remember. Okay, and this is another one. Okay. That's for number, what's that? Number 42? Oh, no, for number 44.
I have a question, Thomas.
Okay.
This might be a dumb question, but I can't.
No dumb question for now.
Right. I can't see how you got the sine squared t from 1 minus cosine. I don't know how you manipulate that really.
Okay, so
If
are
you
we
could-
okay? Are we okay with this for now?
Yes.
Now what I do is I multiply and divide by 2.
Oh, right. Just because they cancel out, right?
So then in the next step, these two guys becomes 36, and this guy becomes sine squared t.
Let's see. Wouldn't it be a negative inside the parentheses still?
Negative inside the parentheses.
Once you replace that with the 1 minus 2 sine squared t. What happens to the negative 2 sine squared t?
Oh, you mean the one here?
Yes.
Yeah, if you manipulate this, let's move this guy to the left and this guy to the right. So I get 2 sine squared t equals to 1 minus cosine 2t.
Oh my God. Okay, I got it. Thank you.
Okay.
Yeah, now I get it. Thank you.
Hey, it's 9 something. You must be tired.
Yeah, I've been studying a lot for the test on Wednesday.
Yeah, yeah. Don't blame yourself if you, and don't call yourself stupid or silly at this point. You are tired. I know. Number 48. Maybe I do this one more. Maybe I have a couple more questions I would like to do though. Let me do this one first. Number 48. Number 48. Find the length of the loop. Find the length or the circumference, to be more precise, of the loop for this curve. X equals to 3t minus t cubed and y equals to 3t squared. To be honest with you, I don't know how to do this problem. But let me give you what makes it difficult. Okay, they tell us there's a loop. Once you have a loop, it means there's a coordinate. There's a coordinate that hits this, that the curve actually hit twice at different time, at time A and at time B. Okay, you see what I mean? Now then, later on, we need to find the length of this loop. You see what I mean? Now, to find the ds, it's actually quite easy. Let's do the ds first then. Okay, solution. dx dt, that will be 3 minus 3t squared. dy dt, that's 6t. So dx dt squared plus dy dt squared is 3 minus 3t squared being squared plus 6t being squared. That is 9 plus 18t squared plus 9t to the fourth, but that is 3 minus, or 3 plus 3t squared being squared. So the square root of dx dt squared plus dy dt squared is basically absolute of this 3 plus 3t squared. But the expression inside is always positive for any t anyway. Okay, so we are done with the integrand, right? Now, so what is the arc length? The arc length, I hope you see the problem. We don't know from what t to what t should we integrate this. You see what I mean? How do we find the t's where the loop happens? Okay, that's the issue, right? Now then, let's take a look how to find it out. How to find the t's that gives the same coordinate. The x is an odd function of t, the y is an even function of t. Any idea? From here, we see the t's has to be opposite, right? Okay, so y equals to 3t squared. Okay, that's an even function. Okay, dx 3t minus t cubed. Let me factor the t out. Okay, I see what happened. Okay, so t equals to plus minus square root of 3. That will give us x equals to 0. But then the y will be the same, right? We have different t's for exactly the same xy. Okay, so t equals to plus minus radical 3. We get the coordinate 0, 9. Okay, so the integral will be from negative radical 3 to radical 3, 3 plus 3t squared dt. Then from there, you just integrate it. That's an even function. Okay, because it's even function, let me fold it 2 times integral from 0 to 3, 3 to radical 3, and so on and so forth. That's 612 radical 3. So you see, this is the hard one. This is the hard one. You need to find 2 different t's that give you exactly the same xy's. You need to see how the x and the y behaves actually. Number 62. I think I did number 62 in my number 62. I do it anyway. Number 62, we have the curve x equals 3t minus t cubed. The y is 3t squared. Hey, that's the same question we have earlier. Okay, and find the exact area of surface obtained by rotate the curve for t from 0 to 1 around x-axis. Okay, let's see the idea first. Suppose this is the curve. I want to rotate that around x-axis. Okay, so what is the surface area? That will be the ds rotated with radius y around x-axis. Okay, so the surface area will be 2 pi integral from a to b of y ds. Do you remember that? Now the y is, so surface area equals to 2 pi integral from 0 to 1. The y is 3t squared. And the ds, well, we actually computed earlier. This is the ds. I mean, happened to be the same with what we did in number 48. Okay, see number 48. by coincidence. I didn't plan it, but then the ds was, what is it again? 3 plus 3t squared. 3 plus 3t squared dt. Oh, that's Mickey Mouse. That's 18 pi integral or t squared plus t to the fourth dt from 0 to 1. That's 18 pi 1/3 plus 1/5. 144 over 15 pi. Cute, nice. How about number 66 then? If you rotate that around the y-axis, we have the curve x equals e to the t minus t. The y is 4e to the t over 2. The t from 0 to 1. Let's see first. Let's say this is the curve. This is my ds. Rotate with around y-axis. That's my x, right? That's my radius. So the surface area will be integral from a to b of 2 pi x ds. Let's find out what is the ds first. dx dt dy dt so dx dt squared plus dy dt squared is e to the t minus 1 squared plus 2e to the t over 2 squared. E to the 2t minus 2e to the t plus 1 plus 4e to the t. Oh, okay. That is e to the t plus 1 being squared. So the square root of that equals to e to the t plus 1. Again, supposed to be in absolute value, but e to the t is always positive, plus 1, which is positive. This is always positive. So the surface area of revolution now becomes integral 2 pi integral from 0 to 1. I think that's from 0 to 1. Okay, what's my x? My x is e to the t minus t. My ds is e to the t plus 1 dt. That's it. Okay, anything after that is technique of integration. Okay, yeah, you do it yourself. Now that's for 10.2. It's quite heavy. 10.2 is quite heavy, but 10.3 is on the easy side. It's supposed to be a review. Basically, how to deal with polar coordinate system. the idea is, let's say we have rectangular coordinate system, coordinate x, y. We will represent that as in r theta. This is the r, this is the theta. So the blue one is in rectangular, the red one is in polar. We want to do this conversion, x, y in rectangular coordinate system equals to r theta in polar coordinate system. Okay, we will learn the conversion first. Now it is by doing the following. The length here will be y and the length, this is x. So we can see that x is equal to r cosine theta. The y is r sine theta. That's to convert from polar to rectangular. If I give you r and theta, if you have the r, you have the theta, you will get the xy by using these formulas. The ambiguity happens when we have rectangular going to polar. If we have rectangular to polar. Suppose I give you x and y, how do you find the r and theta? The r is easy. The r is actually square root of x squared plus y squared. Now from here, we have something you don't like, which I don't like either. The r may be negative. In other words, we accept the r to be negative. R squared equals to x squared plus y squared. R may be negative. And this is the fact that I hate the most. R may be negative. How about the theta? The theta is equivalent but not necessarily equals to tangent inverse of y over x. Okay. The problem is actually here. There are some multiple r theta for the same xy. Now let's do conversion from polar to rectangular first, the easy one first. Conversion, for example, again, this is a review from your intermediate, this is a review from your trigonometry. So for example, I do number 3. I believe I did number 4 in my lecture. So number 3, find the rectangular coordinate system. Part A, 1 comma pi. One comma pi. So the x component is radius 1 cosine theta. That's -1. Y is 1 sine theta. R sine theta. That's 0. So the coordinate is, this is in polar. The rectangular will be -1 comma 0. Actually, you can just look at that. The coordinate system. The angle is pi. The distance from origin is 1. Right? So the coordinate here must be -1 comma 0. Right? Happens to be a nice angle. Now from here we see that if we have polar coordinate system, the rectangular coordinate system is unique. Part B. 2 comma -2 pi over 3. X is 2 cosine -2 pi over 3. That's 2 times what? -1/2. For y, that's 2 times sine -2 pi over 3. That's 2 times negative radical 3 over 2. So the polar coordinate 2 comma -2 pi over 3 is -1 negative radical 3 in rectangular coordinate system. Now part C. The one you don't like, I mean, I don't like this. See that you give us radius negative. That gives us a very big ambiguity, by the way. What will that be in rectangular coordinate system? Again, we use the same formula. X is R cosine theta. That's radical 2. Y equals to R sine theta. Oh, by the way, this also implies you need to memorize those special angles. Okay? You need to memorize those special angles. So this is radical 2, negative radical 2. What do I mean by special angles? The one that theta equals to 0, pi over 6, pi over 4, pi over 3, and pi over 2 in quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay. Now those 0, pi over 6, pi over 4, pi over 3, pi over 2 are these angles in quadrant 1. Now then we have reference angle for quadrant 2, 3, 4 also. Now let's take a look on number 5. This is where I said earlier we have ambiguity. Number 5, find the polar coordinate system. The polar coordinates. part A. So we have 2, comma, negative 2. That's in rectangular, right? Let me show you first what we can do. 2, comma, negative 2. 2, comma, negative 2 approximately here. The distance from origin is 2 radical 2. I mean, you can just use Pythagorean theorem. Okay. Now then, the angle here is 7 pi over 4. Okay, so one way to represent this coordinate, this polar coordinate, is 2 radical 2, that's the radius, and the angle 7 pi over 4. The one we don't like is that we may go the angle clockwise direction. This is negative pi over 4. So the ambiguity is that for the same coordinate 2, comma, negative 2, you have more than one way to represent that in polar coordinate system. 2 radical 2, negative pi over 4. It will give you exactly the same position. In fact, we can also see it this way. We can also see it this way. Like the coordinate 2, comma, negative 2, we can go in that direction, okay? But I shoot the r to be negative. So take this angle here, but make the r, the radius, to be negative. Okay, that angle is 3 pi over 4. Right? That angle is 3 pi over 4, but I choose my radius shooting backward. At this angle, I'm supposed to shoot on the top left. But if I want to shoot bottom right, I make my radius to be negative. So we can write this as negative 2 radical 2, comma, 3 pi over 4. I really hate this so much. Okay, I already say this word. I use this word hate so much because this is a backstabber. It's like you are trying to shoot somebody there, but you purposely hold your gun backwards so that you shoot the person behind you. You see that? It's like you hold the gun, instead of facing that way, the gun is actually facing backward. I hope now you understand what I mean by a backstabber. You shoot the person behind you by facing forward, but your gun facing backward. Can you imagine that? I mean, it hurts opposite ways, you know? Interesting illustration. To be honest with you, I don't know how to, what kind of words will be better than saying it that way. Because that's what I feel. It's like you shoot backward. You really shoot backward. So imagine Thomas is facing that way. Thomas' eyes are there, but I shoot the person behind me. Right? And of course, beside that, we also have this angle. Negative 5 pi over 4. And shooting backward. Now, I do this question by a lot of intuition. Let's do it formally. Let's do it formally. So r squared equals to x squared plus y squared. Right? That's equals to 8. So r can be seen as square root of 8, or you can also see that as negative square root of 8. If we have a choice, we tend to use the positive branch. If you can choose, we tend, I including, choose the R to be positive. Okay, but here's the issue. What about the theta? How about the theta? Tangent theta equals to y over x, right? Okay, the y is negative 2, the x is 2. Oops, sorry. Yeah, that's right. That's negative 1. So theta equals to tangent inverse of negative 1. No. I cannot write it this way. I'm sorry. Cancel. I cannot write it that way. So tangent theta equals to negative 1. Now, why I cannot write it as tangent inverse? Because once you write it as tangent inverse, then it becomes a one-to-one function. There are two angles theta such that tangent theta is negative 1. There are two angles. Theta equals to 3 pi over 4 or 7 pi over 4. To be more precise, I'm sorry. Tangent theta equals to negative 1 means theta is 3 pi over 4 plus pi k. That's all the theta that gives you tangent theta equals to negative 1. While if you write it this way, you need to settle with only one theta, that is negative pi over 4. I mean, you can use your calculator. You will have only one solution. Because tangent inverse starts with a one-to-one function, right? The only way you can do tangent inverse is by restricting the domain. Therefore, tangent inverse gives you only one solution, right? While we know tangent theta equals to negative 1 has multiple solutions. Okay. In other words, if you use tangent inverse, you get only one angle, negative pi over 4. While if you use tangent theta equals to negative 1, you get multiple solutions, and those are 3 pi over 4, or negative pi over 4, 7 pi over 4, 5 pi, I'm sorry, not 5 pi over 4, 3 pi over 4, 7 pi over 4, negative pi over 4, negative 5 pi over 4, so on and so forth. So basically, if you use these, you get multiple solutions. Now, if you insist using theta equals to tangent inverse of the quotient, you will be forced to get only one solution, which is not true. That's why I say here it's equivalent. You need to adjust with the quadrant. Okay, it's not equals to. It's not strictly equals to. Okay, so this is how this is what it will happen. So tangent theta equivalent to tangent inverse of negative 1, right? So theta is equivalent to negative pi over 4. Now you adjust that. Negative pi over 4 is this direction. Okay, and it happens to be the same quadrant with what we want, right? 2, negative 2. So then you can use that theta. Now, imagine if I change the question instead, the coordinate is -2, 2. Let's say part B, number 5B. Last question before I go. We have -1, radical 3. That's in rectangular. The radius so you tend to say r equals to 2. Okay, fine. If you want r equals to 2, if you want the r to be positive. But how about the angle theta? Theta is equivalent, not equal to, tangent inverse of radical 3 over -1. That's equivalent to tangent inverse of negative radical 3. If you use calculator, it will give you -pi/3. Now the thing is, -pi/3 is here, but your coordinate is actually here. You see that? That's because tangent inverse will only give you quadrant 1 or quadrant -1. It will never give you quadrant 2. So you need to do some adjustment there. Now, you need to do, so that gives you, oh, this is my angle here, right? Okay, but I need that to be in quadrant 2. Then adjust that. Okay, I add pi. So theta equals to now, not equivalent anymore, 2 pi over 3. How do you get the Thomas? You add 180. So this is equal to 2, 2 pi over 3. If you insist that the radius and theta has to be a positive number. But you can also make it -2, -pi over 3. You see, -pi over 3 means you are shooting this direction. Right? You are facing that way, but you shoot backward. Okay, that's for that one. This is for this method. Now, on Monday next week, after your test, I will continue from this 10.3, where we will deal with some polar equations, which I really think you should watch the lecture video. Okay, yeah, watch the lecture videos. I may just do a little bit from there, and then we focus on 10.4. Okay, that's what we will do on Monday. So we'll do, on Monday, we'll finish up 10.3 and then go on with 10.4. Okay, then see you. Yeah, see you. Yeah, don't worry about this, what I do today. Don't worry about this. You don't even need to worry about 10.1. Okay, your test will be up to just what's that, the physics thingy, right? Okay, up to 8.3. Yeah, that's the one you need to focus on. Okay, see you then.